recording it or uploading. Is here.
All right, guys. So, are you guys ready? Are you in the same room or are you in a different room? Think Rio, Aldi, and Ahmed is one room. You're in a go-to room.
Yes, Pak.
Fadel is somewhere else, probably.
Only us, Pak. For Nico and Fadel, maybe they
Okay.
will join
All
the
right.
Zoom at home.
So, should we start?
Yes, Pak.
Hang on, the sound is kind of like distorted.
Kayak orang DPR gitu.
All right. Okay. In one, yeah, it's good.
Apa mending tiga gitu? Apa mending tiga aja?
In one monitor.
Kalau
But
misalnya
if
kalian
if there is any
apa sih?
technical difficulty, like there is no sound or the screen that I'm sharing has stopped sharing, then just let me know, okay?
Aman banget, Pak.
Yeah.
Oh, gitu.
Okay, so let's continue with the class. Yeah. Let's continue with the topic. We've discussed about the first, about the mathematical optimization or engineering optimization in this case. And now we are start to go inside one of the topic, which is a single variable optimization. Yeah. So now we are starting to learn about you can say the simpler one. Yeah, the simpler one, just single variable. Meaning, if you remember in OR or operation research or penelitian operasional, you have several variable like x1, x2. Here we just have one variable. And then how can we solve that? Yeah. So the modeling part should be in the earliest part of the penelitian operational or the operation research. But in here, we try to figure out the solution. Some way that is, you can say, the simpler way to find solution. Okay. And for this purpose, we're gonna discuss about optimality criteria. So how do you know if it's optimal or not? If you don't actually draw the picture of the problem, then how do you understand that if what you're doing is optimal, what you find is optimal or not? Yeah, about the points. Okay, so here, this is the one that we're gonna learn about the type of single variable functions, and then we're gonna learn about determining stationary points, and then classification of stationary points. Okay, right. So several example of a single variable function. We have three types of this: discrete, continuous, and discontinuous. So for the discrete, you can see that it's only points. Either is 0.5, and here for the x-axis a 1, 1.5, 2, and
Masih gampang apa? Tinggal turunan-turunan. Ya. Is the
yeah. While the continuous is the whole line or the curve, like in the bottom section. Yeah. And then there is also a discontinuous function, which is partly in the left side, left top, and partly in the bottom right section. Okay. So this is several that might happen, and it will have different approach in how to find the solution. Yeah. How can we get this type of graph, you can say, or function? It depends on what type, what the parameter, and what type of the variable. Yeah. Say for discrete, it's you can say that it's not continuous. That means, for example, of the data that are discrete, it could be some of the integer programming, like the number of people or number of certain configuration that is only 0.5 comma 1, only 1 comma 2, and so on. There's nothing else. While the continuous is more likely to be a flow of something. Yeah, a kilogram that can be decimal as well, or a flow of a water, how many debit of the water, yeah, or cubic, and so on. While this continuous is similar to continuous, but like a curve, but it's separated in like the picture. Okay, here, then
Clear, Pak.
we have, yeah, okay,
Sorry, I said clear, Pak. Sorry.
okay, yeah. So now we have different type of function. We have what we call a monotonic function, which monotonic function, if I can read this, is a function f(x) is said to be monotonic, either increasing or decreasing, if for any 2 point x1 and x2, with x1 is less than equal to x2, it follows like this. If x1 it's less than fx2, it says to be monotonically increasing, while if it's fx1 is greater than fx2, it is said to be monotonically decreasing. And this is the sum of the example, whether it's continuous, the curving, or like a step. Yeah. So in here, there's a function, just one function, which has x1 and x2 in here, while the x is the x-axis, and the y-axis is fx, so a function of x. Yeah. So the fx when it's x1 is here, somewhere in here, while the fx when the x is x2 is above it. Yeah, that means the fx2 is greater or bigger than fx1. It says to be monotonically increasing. Yeah, while the decreasing is the other way, is decreasing. The fx1 is greater than fx2. Okay, this is a definition that it used to make us easier when we analyze. Yeah, because x1 and x2 could be anything. It's a sample that we want to find out. So what is optimal? Which section that has the optimality? Which x1, which x2? It could be a lot of probability, whatever it is, x1 and x2, and we just need to know, is it increasing, monotonically increasing, or monotonically decreasing? Yeah, as a part of uh, understanding more about the process of optimization that we are doing. Okay, and there's another one what we call a unimodal function. Okay, so I'm gonna read this. A function f(x) is said to be unimodal on the interval a to b, so x is between a and b, and if it is monotonic, so it has to be monotonic on either side of the single optimal point x star in the interval. So we have this, say, this curve. This has the x-axis, as this is the y-axis as fx, and we have x star, for example, in here, exactly at 0.0, for example. Yeah, and then this curve is between interval a and b, which we don't really see where is a and b, somewhere in between here and here, for example, could be anything. And that interval, sometimes you're the one who define it, because you're the one who want to search where is this x star, because this is the optimal one. Yeah. In other words, if x star is the single minimum point of fx, so here, single minimum point, there is no more point that is less than this x star, yeah, and the range between a and b, and it's somewhere in here between a in the left side and b in the right side, then fx, this function, this curve, is unimodal on the interval a and b if and only if for any 2 points x1 and x2 we have applied this. If in any point x1 and x2 x star is less than x1 and less than x2 implies that fx star is less than fx1 and
Is it the person that pay for your tuition? The one who pay yesterday? Yeah. Oh, but is like the person you choose? Is it the same as like when you ask about your scholarship? Right?
this because
The
then
person who's the name?
we know that x star is the lowest point.
But you told me before.
Yeah. Fx star in this condition, sorry, in this condition, and fx star in this condition is always the lowest. Yeah. Whether x1 and x2 is more than x star or x1 and x2 less than x star, the fx star is always the lowest. Then
The government.
it will make this curve because whether you go to the right or to the left,
Oh, in the bus.
fx is always getting bigger like
Dia tu
this.
naik
The
bus.
only smallest of fx is exactly in the middle of f or x star. Okay, so this is what they call unimodal, and then apply this. Okay, whether it is x1 and x2 more or less than x star, fx star is always the lowest. Okay, unimodal. So we want to find this unimodal actually because it's good. We can find the optimal one because if it's not unimodal, it's a bit hard. Like if you want to say you want to find where is the minimum, don't know that don't know the function. Is it unimodal? Then if the answer is yes, it is unimodal, then you can find an optimum minimum point in this case. Yeah. So there's also a keyword that you want to find out what's the type of the function, unimodal or not. Yeah. You want to find a unimodal one. You want to calculate a unimodal function. Okay. And we also have this basic principle of calculus method on the optimization. Yeah. So you might have a curve like this. The function is like this. Yeah. And in the x-axis and y-axis as fx between a and b. So the interval is between a and b, which, yeah, you have several up and down, up again, down, a little bit up. But you can see some are at the lowest point and other are is at the highest point, while others are in between. You can see, yeah. So we have A1, A2, A3. It's a relative maxima because it's the highest points, several highest points, while B is the relative minimum because it's the lowest points. Yeah, after B1 is increasing. After B2, if you go to the right, it's also increasing. That means it is a relative minimum. And then how about this A2? This is the highest. It means this is the global maximum because there's no other point that is higher than this. While B1 is the global minimum. Yeah, because there's no other point that is lower than this. Yeah. How about this? There are other word about this A1, A3, B2. Yeah. It's called a local, not global but local. Like A1 and A2 is local maximum, while A2 is global maximum.
Put like the words is good. Look at this. All of the scores of my friend. So one of them got 68.
B2 is
Again 68. Again 60. 44. Then 68 again. 42.
G somewhere in the right, then we might have several new local maxima, minima, local maxima, or even global, new global maxima. It depends on what's the interval. and this is what we want, what we are looking for. Yeah. This is multimodal because not just one, but multiple uh, points that are max or min. Okay. And yes, and this is only made by one or a certain function, right? Certain function, and only one variable, which is x. That's all. Fx is just the function of x. Yeah. It's not that this is x1 and this is x2. No, this is x and this is fx is different. Yeah, fx is a function of x and x is the variable. Okay, so now we want to find if we have a function and we need to find where is the global maximum and where is the global
Ahmed, you wanna go to canteen?
minima. And then you're gonna ask like in which interval this a and b is given, but what if they don't give you interval? And where should you look for? Now that's the trick, right? Because we don't know. Maybe after B in the right side, there'll be something else. But what's the A and B? Yeah. In some of the case in the industry, this is the one that we want usually use or decide which interval is the one that is functional for operational. Yeah, operational or based on the management decision. Operation means before A, it might be something that the management do not really like because it's outside of working hour, for example. The setting is a bit more risky. Also, more on the right of the B is also maybe sometimes that the management do not like, or you as the operator in the say shop floor in a factory. Yeah, more than B is not good because it's more than 5 p.m. for example, or it's the settings of the machine that is too expensive, maybe needing more gas, more electricity. Could be anything. Yeah, could be so many reasons. Okay, but that's what you want to find out. Like first thing first. Okay, this is the function. So what interval are we looking for? What settings that we want to look for? Okay, here. And then the next step is to find out this single variable optimization. In this case is optimality criteria. So there's a theorem that when we follow this and we check, you'll see that is there any optimality or not? In this section, is there any, I don't know, global or local condition without actually drawing the graph? Because I know that if you actually you have to draw the graph when you're in the UTS, something like this, then you're gonna have a headache. Yeah, it takes a lot of time, and this is not common curve. Yeah, you're gonna run out of time by just drawing this in the correct way. And do you want to find out between A and B in this function? Is there any maxima, minima, global, local, or anything? That's why we have developed this. Yeah. Two term. First is necessary conditions. Necessary means you have to have it. You know, this condition for x star to be the local minimum or maximum of a function fx on the interval a and b is if we use a differential of fx star is going to be equal to 0. Then you'll see that there is a local maximum or minimum. Yeah. Here, if equation 2, 1 is satisfied or the differential of fx star equal to 0, then x star is a stationary point of fx, meaning that certain point is a spatial point. Stationary point mean could be minimum, something that is minimum, or maximum. Or we can say something else that's called saddle point.
No.
Yeah. We'll see in the next slide. What is that? A point that is an optimum candidate must fulfill the necessary condition. First, check this. Yeah, use different shade, the fx star, and this is what it means. The stationary point is here. Could be global minimum, could be inflection point, in which is you can see the different curve between the left side and the right side. It is inflection point or a global maximum or local minimum, could be anything. This is stationary points, the one what that we are looking for. We don't know it yet. Is it global minimum, global maximum? We don't know it yet. But we know that these points are the special one, the stationary one. Yeah, the one that change. Okay. And then after we find the stationary points, then we do the check the theorem 2, which is sufficient condition. Suppose all derivative of a function up to order n minus 1 are 0, and the nth derivative is not 0. It means like this. Derivative is to f accent is the derivative. Yeah. And the order is how many you do it. Once or two accents. Yeah. Or three accents. That's the nth. Yeah. Suppose all derivative of a function up to order n minus 1. So if it's n is 2, that means the order is actually this. Okay. This is f n minus 3, sorry, n minus 1, which is 2. Derivative of 2. Yeah. Is equal to 0. Here. F derivative of n minus 1 order of the x star is equal to 0. And the n1, but the n1 after n minus 1 is not 0. Okay. So when you do the first theorem, you just do it once, derivative of this. And then you do it again, the second derivative, see if it's still 0. Until the third, the fourth, I don't know. Just until you reach that it's not 0 anymore. Okay. And while the f derivative of uh, f derivative n is like this, the mathematical function. Then you're gonna want to know how many times have I do the derivative. Yeah. What is the n1? That is not 0 anymore. If n is odd, meaning 3, 5, 7 is odd, right? So you do it until 5 times of the derivative. Then x star is a saddle point or inflection point. If n is even, say 2, you do derivative, and the second derivative f x star is not 0, or the fourth, or the sixth, then x star is a local optimum. Could be maximum, could be minimum. Then we can check again. If the fn x star is bigger than 0, then it's a local minimum. But if fn x star is less than 0, then x star is a local maximum. Okay. This is the efficient condition. Okay. Any question up to this point?
Gue pindah dong, gue pindah dong, gue pindah. Gue pindah.
If not, I'm going to continue, and maybe it's going to be better if you see the example. Yeah.
I have a
But this is
question, Pak.
yeah, okay.
So based on the theory for the industry real world problem, what do we have to find? Is it the maximum or the minimum for it?
Depend what we're looking for. Depend on what we're looking for. This is also because this function is also what kind of function. In the OR operational research, you learn about how to make the function to model, right? But in here, it depends. In this case, it's up to us what we need to find. Yeah. And this is checking. checking the X star, whether it is local, minimum, or maximum, or not at all. Yeah. Or a saddle point. Yeah. Maybe if we are looking for a maximum, say we want to look for a global maximum, and we find an X star and we check, oh, X star is actually local minimum. Could be. Yeah. It is a stationary point, yes, but it is not a global maximum. That means you need to find other interval or other condition to find the global maximum. Yeah, like that. Okay. Say the global maximum is what? Profit? Yeah, for example.
Oh, and also,
Okay.
Pak, does the curve on this single variable optimization for multimodal, does it correlates with the time? Like each, if it's like higher in each time zone maybe, or
Could be.
it could be.
But mostly X is just one variable. So if it's time, that means X is time. But if X is not time, then it's not related to time. Yeah, depend on the variable. Like if you remember in the OR, the number of people, the number of raw material, the number of product to produce could be those things, and those are not times.
And what makes it actually like impact the curve, Pak?
Which one?
Like for example, like profit, if it's going down, what does it mean? And if it's going up, what does it mean? Like the maximum or the minimum?
Okay, so say the profit is fx,
Anjir
yeah,
FX.
and x is, you can
Variable
say,
paling
like,
profit hijau.
hmm, the number of product. I just make it easier.
Oh,
Yeah, the number of product. Even though this curve is a bit complicated for just one, but just if the number of product is too low, then it's a bit expensive. But if you increase the number of product, then you actually reduce costs. But if you keep increasing, then increase the cost until the global maximum if it's cost, yeah. But then if you continue again, gonna be reduce the cost. So this is one example to find out. So how many products should we make based on this graph to reduce to have the minimum cost? And you should find this one. Your goal is to find the global minimum. Yeah. But if this is not cost, but if this is profit, then you want to find out this global maximum, right? This is a high. So it depend what is fx. Okay.
okay. Thank you, Pak.
Johan, if you have any more question.
Thank you,
Okay. All right. So sufficient, and this is just a theorem, but we have steps of our algorithm with analytical approach mechanism for getting a solution. This is from two different reference, but basically it's the same. Yeah. With this problem to minimize, for example, fx with constraint x is between a and b, because that's what we're looking for. The first one from reference, step one is to apply necessary condition, which is just the derivative of df per dx equal to 0 to find all stationary point, and then apply sufficient condition to those points. So these are x stars, yeah, in the range, and then compare the value and determine the global minimum because this is minimum. Or in the other word, this is another step from different reference. Same to find stationary point here, derivative of the f where the x equal to 0, and select all stationary point that belong to the interval a and b, call them x1, x2, and so on. Yeah, this x star to make a note that we know this x1, x2, and so on. And this point along with a and b are the only point that can qualify for local optimum. And then, because they are stationary points, they could also be a inflection point, saddle point, yeah, which is not maximum or minimum. And then find the largest value of fx out of a, b, x1, so on. And then this value become the global maximum point. Since this is a minimum problem, then the one that has the largest value, since this is is it minimum problem, become the global maximum. Is it or hang on? Oh, this is for this is the other way around. I think this is problem. This is explanation for maximization. This is for minimization. Yeah. Because this is global maximum. This is global minimum. Yeah. So to find the global maximum, this value has to be largest value of fx. If it's the lowest value of fx, what it means is the global minimum. Okay. All right. So yes, could be differentiable or derivative of it. If it's not differentiable, the necessary and sufficient condition cannot be applied. Yeah. If you cannot use derivative, but you can use other method. Okay. So let's go then to one of the example. The simplest one. Fx is equal to x cubic. Yeah, the power of 3. So let's find out. How about fx is 0? Well, let's find out all the stationary point. Before finding the x is 0, I mean, let's find out the stationary point. Let's do the derivative. The f per the x, yeah, is equal to 0 when x, if it's equal to 0, what is the x? Yeah, this is the first theorem actually. See, the derivative of x, the power of 3 is 3x squared, right? 3x squared. And if 3x squared is equal to 0, what is x? X is 0. Yeah, x is 0. It's first derivative. So this is x is 0 is stationary point. Okay, let's do it again. Let's do the second derivative. It was 3x squared, right? 3x squared, if we move the derivative again, it's going to be what? 6x. Yeah, 6x. Okay, 6x. And if x is 0, it is still, if it's x is 0, then the second derivative is also 0. But then until you find out, try to do again the derivative the third time, it's not, there is no x anymore. You run out of x. Only 6 now. Yeah. It was what? 3x, so 6x. 6, the derivative of 6x is 6. So now it's not 0 anymore. Okay. So first you see that, okay, this is a stationary point. But what kind of stationary point? And we do derivative until the third time, which is n is 3, the order is 3, which is odd. Here. The n is 3. 3 is odd. That means when the x is 0 or the x star is 0, it is a saddle point or inflection point. It is not local minimum, it is not local maximum. But it's only inflection point. Or if you actually draw it in a graph, it's like this. This is the graph of x power of 3. Yeah. And x0 is just the inflection point or saddle point. Not maximum, not minimum. Okay. So this is how you find it. You first you have a function. You want to find all the stationary point, which is apparently only one stationary point. Yeah, because x is only 0 when this is 0. When this condition apply, x is only 0. There is no other x. And you keep derivating until it's not 0 anymore. And then C, If the order is odd or even. If it's odd, then it's saddle point, inflection point. If it's even, then you need to check. You need to put in the x star, which is the 0, into the fx, then see. Okay. Um, let's go to the other example. Hope it's getting clear. Now we have a completely different function. Yeah. Yeah, like this fx is 5x power of 6 minus 36 power x power of 5, and so on. Okay. You can see this is not linear anymore. So this is not linear programming that you learn in person research. This non-linear one, definitely. Determine the stationary points. So what with this function, what are the point, the stationary point? Check if it's maximum, minimum, or saddle point, if any. And if you just to recall, yeah, what are the rules? First, you need to do a first derivative and make it equal to 0 to find out what are the x star. There might be several x stars, okay, which we're gonna name it x1, x2, and so on. And then we're gonna check again using this theorem. Okay, let's do it. Here, this is the function. The first derivative of the function is this, the f for the x. So 5x power of 6 become 30, x power of 5, right? 36 x power of 5. If you make the derivative become 180 because 36 will divide with 5. And the 5 power of 5 become power of 4. So 180 x power of 4 and so on. So this is what you learned previously in the previous semester, also in SMA or high school probably. Yeah. Until 36, there is no x, so it's just 36. If you do the derivative, that's going to be just 0. There's nothing. So only this. So we have this now. And then we need to make it equal to 0. This. We need to make it equal to 0. So we can find the x star. So this is equal to 0. And this is another way to make it, how can I say? To find out manually what is x, what are the x's. Yeah. So you change from this form into this form. And then how can we change into this? Again, it's math. Basic example until we find the actual rule, but not today. Okay. This is using the yeah, this theorem, these two. Okay. All right. Any question? Sorry, what did you say? Oh, good. Okay. So example 4. This is the result, but there is no specific answer. So this is the key, but I wanted to try later on at home just for practice. Okay. Yeah. Just help with this dfx. Derivative first, the first derivative of fx, but then we need to process those term 1 and term 2, and let's see if your result is the same or different. Oh, this is Indonesia, sorry, but you know what I mean, maximum or minimum. Yeah, let's see if your are the same or different, okay, for practice purpose. Yeah, okay, so this, and next week, topic, okay. Sorry again that I Did I send you the previous file?
Um, I think already sent, Pak.
Okay. So here is uploading, and there you go. It's in the chat. Download it and check again. Okay, you got it? Okay, all right. So once again, thank you. And I'll just close the Zoom. All right. You have a good day, guys.